so we have our graph. We're going to set up our graph by looking at the membrane potential over time, because we know what we're talking about when we're talking about an action potential is a change in the membrane potential. So the membrane potential, remember, is the difference in voltage from the inside of the cell to the outside of the cell. And our action potential, oh no, is a big spike in charge. All right, I'm gonna have to clear that. Okay, so our membrane potential on the Y, time on the X. So I'll just write millivolts here. We have time over here. Okay, so one of the things we want to keep in mind as we're talking about our action potential is we have a couple of special numbers. So one is that we know that our resting membrane potential is -70. So I'm going to mark that here. So I have a resting membrane potential of -70. Okay. We have a threshold we're trying to get to. So a threshold we're trying to get to of -55, which tells us once we reach our threshold of -55, that's when we're going to set off the action potential. So if we don't get there, we won't have an action potential. And then we want to also kind of keep in mind a little bit that part of what's influencing this action potential is the equilibrium potential of sodium and potassium. So we might also add those on here. It's fine if you didn't, but it's helpful to think about as we're thinking about what's flowing. So our equilibrium potential of potassium would be down here. Be like -94. And our equilibrium potential for sodium would be somewhere up here. Would be about +60. Okay, so now I'm going to actually do the drawing part. Okay, but we're set up with the numbers we're trying to reach. So our action potential starts out at rest. So we start out at rest. We have just a normal neuron hanging out here. Then we're going to work up to our threshold. Our threshold depolarization because we're moving away from -70 in a positive direction. So we get up to 55. The way we would do this is by having graded potentials that potentially add up to this number. So we have a certain amount of sodium flow in response to stimuli, gets us to -55. And once we hit -55, we have all these voltage-gated sodium channels start to swing open. They swing open more and more and more, faster and faster and faster. Oh, probably shouldn't have drawn that up that high, so this is no longer up to scale. But they open up because their activation gates are opening up, and that brings our charge to +30. Okay, so we don't get all the way to the equilibrium potential for sodium. We get about a little over halfway there, right? We've gone up a whole 100 millivolts at this point. It's 70 to get to 0 and then another 30 more. So this is a big spike. Okay. Now we have our delayed action on the voltage-gated sodium channels. So this is about a millisecond after we've hit this threshold depolarization. So now our inactivation gates start to swing closed. So because our inactivation gates are swing closed, this means sodium can't get through those voltage-gated channels anymore. So this charge starts to drop down. And at the same time as those sodium channels are closing, our potassium channels, they were also on a time delay and they're opening. So we know that during this time phase where we have sodium no longer coming into the cell. The reason we're getting negative is because we have potassium flowing out of the cell. Okay, and then we actually overshoot a little bit, so we get a little below -70, and then eventually we'll come back up to our resting membrane potential. Okay, so this is what your curve that you drew should look like. And now let's talk about the labels. So we have names for each of these phases. So we started out with our rest, right? So our resting phase would be here at the beginning. And so rest is really when we're at -70. As we get from -70 to -55, that's already a little bit of depolarization happening. That's getting to our threshold depolarization. Okay, so our next phase from like, I'll draw some markers, like here, here. Okay, so this next phase, we're going to call depolarization as we get positive. So we have our depolarization happening as we're on the rise. So depolarization is making us more positive than our resting membrane potential. But then our sodium channels close, so sodium isn't flowing in anymore. Potassium is flowing out. We're rushing back down towards this equilibrium potential for potassium. So this is our repolarization phase. Okay, so repolarization is swinging down. And then we can see that we have that little bit of overshoot, right? So we got all the way down to -70, but then we can see that there's a period of time where we're below that. So about here. Okay. This is a period of hyperpolarization, so we might just refer to it as hyperpolarization. But in your textbook, you'll also see it referred to as after hyperpolarization, to make sure we know that this is a hyperpolarization that's happening after the action potential has fired off. Eventually, we'll get back to rest again at the end. Okay. I think I have one person in the waiting room. I do. Okay. Questions at this point? We have a couple more pictures of this graph. We went over a couple different ways we could think about this on Friday, but we're gonna keep thinking about this. This is really the key thing. This is what we've been building to. This is why we bothered talking so much about our membrane potentials, our electrochemical driving forces, is because that's really setting us up for this wave that is how our nerves signal to each other. Okay, if that's it for the beginning, we'll move forward with our action potentials. Okay, so when we left off, we were talking about the fact that our action potentials are these changes to the membrane potential, these sort of whooshes, waves of charge that we're sending down our axons to signal. So a membrane that can send off an action potential is called an excitable membrane, and our action potential itself, we could refer to as a rapid, large depolarization that we're using for communication. Okay. So when we're talking about our neurons, which is where our action potentials are going to be happening, our action potentials are traveling from the cell body to the axon terminal. So we're starting in the cell body or the soma. That's where we'd be receiving our stimuli, those graded potentials. Then the action potential is getting sent out down the axon. So a way that we can think about our action potential, we're going to see a couple of different sort of maps or steps that we can look at it as we're trying to figure out what's going on with the action potential. These are all kind of just different graphs, different charts of the same thing happening, hoping one of them will click with you. Okay, so this is just showing us what's going on with that depolarization phase of our action potential. So the depolarization of an axon is all dependent on that first depolarization stimulus. So that depolarization stimulus is, we have an excitatory stimulus coming in, causing a graded potential at the beginning of our axon and the axon hillock. So we have that accumulation of charges until we hit -55, okay? We hit -55, and that has two effects on our axon. One is that our voltage-gated sodium channels are opening, okay? This causes more depolarization as sodium rushes into the cell. So that's causing that peak depolarization. So that really characteristic part of our action potential, that peak, that +30 charge we're building to. The other thing that's happening as a result of hitting our threshold of -55, that depolarization, is that on sort of a time delay, we're opening up our potassium channels. So voltage-gated potassium channels also open, but they're kind of slow. So our sodium rushes in first. So we can see that happening, number one. But eventually our potassium channels get their butts into gear, they open up, which means that now potassium rushes out of the cell, bringing us back down to our threshold. Okay. So that's just an illustration of what's going on with these gates as we're looking at this depolarization during the action potential. Okay. So we also saw that this chart once before of the action potential as it relates to the permeability of the membrane to sodium and to potassium. So remember, a membrane that's more permeable to something, that means it has more channels open for it, and that also has the effect of bringing us closer to the equilibrium potential for that ion. But as we're graphing here, the permeability to sodium and the permeability to potassium, we want to remember that's really just telling us about whether those voltage-gated channels are open or closed. Okay. So at rest, our membrane is more permeable to potassium than to sodium. We have more potassium leak channels than sodium leak channels, which means that our membrane potential is closer to the equilibrium potential for potassium. So we can see here this, sorry, both the permeability lines are blue, but this one here with the lower peak is our line for the permeability of potassium. So we can see if we compare that to our line for the permeability of sodium, when we start out, we're more permeable to potassium. Okay. But then we have changes to the permeability as we move through our action potential. Okay. So our graded potentials bring us to the threshold. So our threshold of -55. We can see that -55 is more positive. It's a depolarization than our resting membrane potential. So we can see that already our membrane is more permeable to sodium. That's how we got to this threshold depolarization, is we allowed sodium to get into the cell. Okay. Once we hit that threshold, this is a trigger for the rapid opening of lots and lots and lots of voltage-gated sodium channels. This is regenerative, it's positive feedback. So what we mean by that is once we have one voltage-gated sodium channel open, it makes it more and more likely that the sodium voltage-gated sodium channels next to that original channel will open, because as one voltage-gated sodium channel opens, we have a bunch of positive charges moving in, and that local area of the membrane is going to become more and more positive more and more rapidly. Okay, so eventually this brings us to our peak of +30, at which point our kind of slow closing doors start to close. So we have our inactivation gate for the sodium channel. That was on a sort of 1 millisecond delay, so it starts to close, so we can see our permeability to sodium going down. And our potassium voltage-gated channel is also on delay. Its gate is opening, but when its gate opens, we don't have potassium come into the cell because potassium wants to get out. Potassium wants to make the cell more and more negative. And we talked about how we set that up with the electrical driving force and the chemical driving force on potassium. Okay, so as those gates open, we can see that our permeability to potassium is rising again. So this repolarization phase, I would say, is the part where we have the most complexity going on with the permeability to sodium and potassium, because this repolarization is kind of due to both these factors. So if we still had sodium channels open, this influx of sodium could potentially balance out the potassium rushing out. But repolarization can happen because at the same time as we have potassium rushing out, the flow of sodium in is stopping because those inactivation gates are closing. So it's really these two voltage gated channels kind of working together at this point. Okay. So that's our repolarization. Then we have this after hyperpolarization. So this hyperpolarization that's happening after our action potential has fired off. So for a little while, our voltage gated potassium channels stay open. Because they stay open, this means that we're a little more permeable to potassium than we usually would be. Since we're a little more permeable to potassium than we usually would be, we're a little closer to the equilibrium potential to potassium than we usually are, which means we're hyperpolarized, we're a little more negative than usual. So that's what's happening in this dip after our action potential. Okay. And this is important as we start to think about how frequently our action potentials are going to fire off. And we'll talk about that in a second. Okay. But eventually, we're going to get back to normal. So we have our sodium potassium pumps going. We remember that they're pushing sodium out, pulling potassium in. So they basically restabilize our membrane potential through active transport of sodium and potassium. So that would be happening somewhere over here. Okay. So if you highlighted or drew in different colors on your graph at the beginning of class, hopefully it would look something like this. We had basically three phases. This phase one, where we have our rapid depolarization. This phase two, where we have our repolarization. And then this sort of third phase where we have this hyperpolarization, this after hyperpolarization. Okay. So this after hyperpolarization is happening because the repolarization actually overshoots. The number isn't super important here, but we do get down to about negative 85 millivolts here before the sodium potassium pump manages to restabilize us, get back to the resting potential. As we're getting back to our resting potential, those voltage gated potassium channels do start to close. They were a little slow about it, but they don't remain open forever. Okay. This brings us to an important concept about the action potential, which is something called the all or none principle. Now, when we're sending signals in a brain, sometimes we want to send a stronger signal. Sometimes the signal is more important. But we don't actually do this by changing the size of the action potential. An action potential is an action potential is an action potential. They're all the same. They have the same amplitude. So they always peak up to positive 30. They're also the same length. You can see that these action potentials are all kind of identical. Okay. So whenever we hit that threshold, whenever we hit negative 55 millivolts, this is the minimum depolarization to induce an action potential. But it also doesn't matter if we manage to depolarize the cell. Sorry, guys. I'm gonna put that dog away. Sorry about that. Okay. So no matter how big or small our depolarization is at the beginning with those graded potentials, it's if it hits that threshold of negative 55 millivolts, it's going to fire off an identical action potential. So if our graded potentials get us to negative 55, that's called our threshold depolarization. We set off an action potential. If our graded potentials depolarize us a little bit, get us to negative 60, it's not going to send off any action potential. It's not going to send off a little one. It's not going to send off a short one. If we don't reach the threshold, nothing. That's the none part of this all or none principle. If we set off a super threshold depolarization, so that would be like if instead of getting to negative 55, our graded potentials got us to negative 50 or negative 40, doesn't matter, sending off the exact same action potential. It's not bigger, it's exactly the same. That's what we mean by all or none. It's that an action potential is a yes or no, and it's just, did we hit negative 55 or did we not? So every action potential from that threshold level to the negative 55, or a super threshold stimulus, if it got us a graded potential that added up to negative 40, whatever, they're all going to be the same size. So the action potential, if we measure it from the resting membrane potential all the way to the peak of the action potential, it's 100 millivolts. So 70 to 0 is 70, then plus 30 gets us to 100. So every action potential is that size. Okay. So that's what it's showing us here, is as we fire off stimuli, if we reach that threshold, we are always firing off an action potential that's exactly the same. It doesn't matter if we have this sort of medium-ish size stimulus or this super big stimulus. If it's big enough to hit that threshold depolarization, we get an action potential. Okay. So this is just basically rephrasing that. So once we hit that threshold depolarization, an action potential will happen no matter how big our stimulus is. It's not going to affect the size of the action potential. We will see that what we vary eventually when we're trying to send different types of signals is what we can vary is how close together these action potentials fire off. So we're never going to fire off an action potential that looks different in terms of the curve. The only thing that we can vary is how fast they get fired off. So how many in a row. And we'll talk about the constraints on that in a second. So this is just bringing this home again. So here we can see some sub-threshold stimuli. So these pink bars at the bottom are just telling us how strong the stimulus is. So remember when we say a stimulus is weak or strong, we're talking about how many channels it opens in the membrane of the cell body, basically. So how much of a difference to the membrane potential that makes. So we can see we have two sub-threshold stimuli. They don't get us to negative 55. So we would have no action potential. A threshold stimulus gets us to negative 55. So boom, we have an action potential. This super threshold stimulus also gets us to negative 55. So boom, we have an action potential. But this one, action potential is the same as that first action potential. They look the same. They get to positive 30. We don't like shoot up higher just because the stimulus was stronger. So we're going to take a look now at what this looks like. Okay. So that is what our typical normal action potential looks like. It's what every single action potential that we fire off down a neuron is going to look like. So we can look as well. Okay. We can look at this as a map, and I recommend trying to draw out this flowchart on your own. Honestly, as many times as it takes for you to understand it. This flowchart is really comprehensive and pulls together all these different factors that we're tracking. So as you're studying for action potentials, I recommend drawing graphs of the action potential and then also trying to write this flowchart in words. Okay, so we're going to run through it. Oh, why this looks different than it did before. Oh, actually, I do know why. Okay. Okay, so if we start with a threshold stimulus, when we're tracking our action potential, that threshold stimulus takes us, depolarizes us to negative 55 millivolts. So our threshold stimulus will be excitatory. Excitatory means it makes our cell more likely to fire off an action potential. It's letting some sodium into the cell. It's depolarizing that membrane. So we depolarize to threshold, which is negative 55. The first thing that happens in response to the depolarization is that we open sodium channels. So our sodium channels, the voltage-gated sodium channels, are opening because we had an activation gate that was shut before, now it's open. Our inactivation gates started out open. So now both doors are open, sodium can get into the cell. Our equilibrium potential for sodium is positive 60, so we know that sodium wants to move into the cell. So it does so, depolarizing our membrane more and more. So it's increasing our membrane permeability to sodium, allowing sodium to flow into the cell. Sorry, something's really off about this image, but that's how we're stepping through. Okay, so sodium is flowing into the cell. This means that we have a net positive charge in our cells, so we have depolarization happening. This is a positive feedback loop because as we depolarize parts of the membrane, that makes it more and more likely that more and more voltage-gated sodium channels are hitting that depolarization threshold and opening. We also have a delayed effect, and we actually have two delayed effects of the depolarization of the membrane. So our first delayed effect is that our sodium channel inactivation gate closes. So the depolarization of the membrane opened the activation gate, and it did that first. And for a while, the only effect we had was that activation gate was open, so we allowed sodium to rush in. But we have this slow door, this inactivation gate, it closes after a millisecond. So as these sodium channel inactivation gates close, this means that we're bringing the permeability of the membrane to sodium down. So our membrane is becoming less and less permeable to sodium as more and more of these inactivation gates swing closed, which means that the sodium flow into the cell is going down. So a thing to note about these flowcharts, and we'll see lots of flowcharts like this in the future. So be careful that you note the arrow and the direction of the arrow next to the text. So here it says sodium flow into cell, but we have a down arrow. So what it's telling us there is that we actually have less sodium flowing into the cell. Okay. So just be careful that you notice the details like that. All of these other ones were positive. It was increasing these things, which is why I didn't mention it before. Okay, but right now we're closing these inactivation gates, bringing down membrane sodium permeability. So we're slowing the sodium flow into the cell. Sorry, this is really horrible. Okay, what's happening now is that we are basically going to start to allow repolarization to happen because we're going to stop making this cell more positive. We have our second effect of depolarization on the membrane, this delayed effect. Our second delayed effect, I should say, is that after a millisecond, we are opening potassium channels. So as we open our potassium channels, we increase membrane permeability to potassium. And remember that our equilibrium potential for potassium is low, it's negative 94, which means that as we increase membrane permeability to potassium, we're going to have potassium flowing out of the cell. Okay, so we have potassium flowing out of the cell. And here we can actually see what it says in that box, sorry. We now have the net positive charge in the cell decreasing. So this is due to these two factors working together. It's that we have a decrease in the sodium flow into the cell, and we have an increase in the potassium flow out of the cell. So we don't have positive charges coming in anymore, but we do have positive charges flowing out. This is a negative feedback loop, and we consider it a negative feedback loop because it's basically shutting down this action potential, right? The action potential was this positive spike in charge, taking us away from our resting state. And as we pull that action potential back down, as we return ourselves to the resting state, that's negative feedback. We remember that negative feedback is basically when we're stopping stuff. Okay. Now, questions about this flow chart? Okay. Yeah, so I want to make sure you practice this because this really has all the facts about the permeability of the membrane, the channels that are open, and the effect on charge, and it pulls it all together. So you should be able to do this, and if you can do this, you should be in good shape for all of the action potential questions on the test. Okay, so we've seen this graph before. This is another way you can study if you're more of a chart person, but I think mapping it out as a flow is helpful as well because it can kind of show you the connection between these facts. But we can see this nice chart of our phases. So at rest, before our action potential, then phase 1, our depolarization, phase 2, our repolarization, phase 3, our after hyperpolarization. So the 3 phases we go through as we're tracking our membrane potential. This chart is also telling us about which channels are open and why, whether it's because of the activation gate or the inactivation gate. It's telling us about our flow of sodium, our flow of potassium, and what's going on with those potassium channels. So this is another way we can summarize all the things that are going on. Before we move forward, I do want to make sure that we kind of remember the difference between our graded potentials, which is where we started out, and our action potentials, which is what we're firing off now. So our graded potentials, remember, were in response to stimuli, and they were happening all the places where we receive signals, which are the dendrites and the cell body. Our graded potentials were pretty weak. They were proportional to the strength of the stimulus. So remember that an action potential is always the same size. Our graph always looks the same. We always have a change of 100 millivolts. But if we looked at a graded potential, maybe it gave us plus 10, maybe it gave us plus 20. It was raising us different amounts close to the threshold, depending how strong the signal was. So we had a weak graded potential, but it did differ in size, whereas our action potential is always, always, always the same. When we were thinking about graded potentials, we thought about both depolarizing graded potentials, so where we have sodium flowing in, and hyperpolarizing graded potentials. So from inhibitory stimuli, opening potassium channels, letting it move out. So we could have a change in either direction for a graded potential. An action potential always spikes positive, so it's always depolarizing. We're never going to have like a reverse action potential that shoots down. It's always the same. It's always this wave of depolarization. So when we're comparing graded potentials and action potentials and we're thinking about whether they add up, for graded potentials, yes. For action potentials, no. No, they're just this one thing. We had different channels involved. We also had some different ions involved. Sodium and potassium are always important for both of them, but sometimes we'll see chloride ions if we're thinking about just the graded potentials. And it is also a thing you should know that they are slightly different in duration. A graded potential is a few milliseconds to seconds, and action potential is more specific. An action potential is 1 to 2 milliseconds. Okay. And that's because they're always the same, so we're not going to see this variation in their effects. So these are questions that you should be able to answer. So I would practice using these as kind of essay questions. I know that you don't have essays strictly on your exam, but being able to explain out a whole process, being able to answer questions like this in your own words is a really good way to make sure that you are ready to answer the questions on the exam. We may come back to some of these as we do review. Okay. So the final topic we're going to get to today is refractory periods. So I said that action potentials, we have this all or none principle. They're always going to be the same. They always spike us to positive 30. So we always have that change of 100 millivolts. That's it. That's what an action potential is. And that's true. So the way we can distinguish between different signals is how fast we fire off action potentials. And there's a limit on that, which is the refractory period. So we're going to talk about what the refractory period is and what causes it. And we're going to see that we have basically two different types of refractory periods, both of which happen after every action potential. But we have one that we're going to call the absolute refractory period. We're also going to see something called the relative refractory period. So these have different implications physiologically. One of them we'll see it is a hard limit. The other can be overcome in certain situations. Okay, so action potentials, the way we can respond potentially to a stronger signal is not by sending off a bigger action potential, but potentially by sending off more frequent action potentials. So sending a beep, 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 beep instead of beep, beep, beep. If you think about the cell receiving, we'd think about that kind of sort of Morse code receiver on the other end. But we can only increase them so far. So the refractory period is this period at the end of an action potential where we can't fire off another one. Okay. So we say that the neuron can't become excited again for a certain period of time. This is why we specified before that we were talking about excitable membranes, because some membranes aren't excitable, and for a little while during the refractory period, our neuronal membrane is not excitable. Okay. So first, we have our absolute refractory period, where we cannot send off another action potential. And important to note here, for our absolute refractory period, is that we can't send off another action potential when we're not done with the first one. Okay, so our absolute refractory period is occurring during the action potential, because at the end of our action potential, our sodium channels are inactive. They're not just closed. At the end, we'll have this inactivation gate closed. So even at the end, as we start to come down, right, during repolarization, we've been closing those sodium channels. We can't fall halfway down during this repolarization phase and then start opening them again. They don't work like that. Once they're going to close, they're going to close. We have to finish that first action potential before we can fire off a new one. Okay. But at the end, we have this relative refractory period. During the relative refractory period, our potassium channels are still open. So we remember that we have this after hyperpolarization here at the end of the action potential. So during this after hyperpolarization phase, so phase 3 kind of, this is going to be our relative refractory period, because we are down below -70. We're even farther than, we're even farther towards our potassium equilibrium potential than normal. Potassium is still escaping the cell. It's holding us down negative. It's basically inhibiting another action potential from happening. But if we were to receive a really, really strong stimulus, we could overcome the fact that we're extra negative right now. So that's why we bother sometimes rating our stimuli as threshold versus supra-threshold, is because we're going to need an extra strong sort of supra-threshold type stimulus in order to send off an action potential during this relative refractory period. So it's not going to be like extra tall. This spike isn't going to be different if we send one off now, but we're only going to be able to respond to super strong stimuli during this period. Okay. Every action potential here, regardless, is going to be a separate all or none event. So we can see just kind of a graph of what this would look like. So during our absolute refractory period, that's happening all of the depolarization phase of our action potential. So as our sodium channels are opening, they're already opening. You can't open them more by having a new stimulus. So this is during our absolute refractory period. We absolutely can't have another action potential because we already have one going. Absolute refractory period also lasts for most of the repolarization phase because those sodium channels have to close. They're closing. You can't open them. The inactivation gate, it's closing. It's going to close. You're stuck. You can't send off another action potential during this time. This is because those sodium gates are inactivated. So the inactivation gates are closed. Can't open them. During the relative refractory period, that's after we fire off this spike of the action potential during this repolarization phase and the hyperpolarization phase. So we're usually almost never going to see another action potential, but it is possible if we get a super strong stimulus. So a second action potential could be fired off really quick and kind of cut this a little short if we had a really, really strong stimulus. And this is because some of our sodium gates are just closed. Some of them are actually inactivated. So remember that the difference between closed and inactivated here is referring to whether we just have our activation gate closed or whether we have our inactivation gate completely blocking the flow of sodium. And then we also have the fact that during this relative refractory period, our voltage gated potassium channels are still open. So we're like extra negative. It's extra hard to overcome that. Okay, so we'll pick up here on Wednesday. Take care, everyone.